Let's begin. So, we're talking about drag again today, but I actually wanted to start by reviewing a couple of the questions that have been on the quizzes. So on quiz 2, there were a couple problems that a bigger percentage of the class got wrong than the other problems. So I repeated them on quiz 4, and I got some improvement, but not as much as I would like. So I'd like us to go over it and make sure everyone understands what I'm trying to teach with these questions. The first one, buoyant force on an object completely submerged in water is measured as X, some force. What is the buoyant force on a submerged object that has the same volume but weighs twice as much? Weighs twice as much.
Same amount?
It is the same amount, Spencer, you're right. But so the first time I gave this question, about 60% of the class got it right, 40% got it wrong. Second time, about 67-33. So there was some improvement. About 7% went from incorrect to incorrect. But I want to make sure everyone understands why this question has the answer it does. So remember that buoyant force comes from the pressure force of the fluid on an object. So for example, if an object is in water, the buoyant force comes from the water. It does not come from the object itself. It is the water pressing on the object. So that means that the weight of the object doesn't change the buoyant force. The volume of it does, because the volume is what changes the displaced water. It changes how much water is displaced, but the weight of the object does not change the buoyant force, right? Which is why the equation for buoyant force is the density of the fluid times the volume of fluid that's displaced by your object times gravity. So if the weight of the object is doubled, but V is the same, the buoyant force is just going to stay the same. So if I tell you the buoyant force on an object is 20 pounds, the weight of the object is doubled, but the volume stays the same, then the buoyant force will still be 20 pounds. Does anyone have any, and that is what I was trying to teach with this problem. Does anyone have any questions about why that is or this concept? Now, Tyler?
Yeah. So wait, what direction is the buoyant force in right now?
So the buoyant force pushes up. The net buoyant force, so it's pressure on an object, it's a pressure force all around the object. But if you put it together into a net buoyant force, it pushes up. Which the reason that is because pressure is bigger, deeper, right? So the pressure is bigger down here than it is up here because pressure is rho GH. So the deeper you are, the higher pressure is. So that means the pressure on the bottom of the object is going to be bigger than the pressure on the top. And so your net buoyant force is going to point up.
So is the rho fluid that we use the average pressure?
It's just the density.
Oh, sorry. Never mind.
Yeah.
What would you do if the density was changing? Would you have to do some type of integral?
Yep, you'd have to do an integral. You'd have to integrate over the whole thing, and it would be more complicated. Okay. So, but there are very few situations where the density will change enough over the space of whatever object you're caring about that you would have to do that. But theoretically, there could be. I don't know, okay. Maybe people are trying to model giant Navy ships or something.
Yeah.
I don't know.
Okay, thank you.
Yes, we do have quizzes. We have lots of quizzes. Quiz 5 opened on Friday. They are on Learning Suite. We talked about them the first day of class. They are on the Learning Suite schedule. If for some reason you did not realize we have quizzes, talk to me and I'll see if we can get you caught up on the first quizzes, okay? Alrighty.
Is it possible for the quizzes to be opened up so we can see the answers and the questions again?
I checked that you should be able to see the answers. It says, I checked the option that says on this date or when you complete it, you can see the answers and the explanations. It's possible that doesn't work like I thought it works, because I thought—
No, they're open now. They weren't yesterday though.
Okay. All right. I may have checked that they open on the end of the due date, but it would probably be better if you could see it right after you take it. So I will look at that and change it. All right. So yes, if you didn't know we have quizzes, get in touch with me. I'll see if you can make up the ones we've had so far. Okay. The second one, tank of area A is filled with water to height H. Pressure force on the bottom of the tank is measured as X. If the area of the tank is doubled to 2A with H remaining the same, what will the pressure force on the bottom of the pool be? And this one, we didn't get as much as improvement as I wanted because it was 48 to 53, 52% before, and then it was 50-50 the second time. All right. The pressure on the tank bottom is just P is equal to P naught plus rho GH. So the pressure only depends on the depth of the fluid. And so if this question were asking about pressure, people would be right that it just doesn't change. But it's not asking about pressure, it's asking about pressure force. And the pressure force on the tank bottom is the pressure times the area. And so if you double the area while keeping pressure the same, you double the force. And the point of this question was to get y'all to be careful and think about the difference between pressure and pressure force. So pressure depends only on H. It doesn't depend on that area. Pressure force does. Any questions about that?
Actually, yeah, I think I got something. So when I read this on the quiz, it sounded more to me like those problems we did where we're talking about the area on a wall that we're calculating the force on.
Well,
both times it came along, it looked like it was just the pressure on the wall instead of on the bottom. And I think that's where a lot of the confusion came from.
Well, the question said the bottom of the tank. So if you read it carefully, you would have realized this. And also, even if it was on the wall, it would actually still be the same. So the pressure, if we're talking about like a rectangular wall, then the pressure force would be the net pressure force. So we're assuming atmosphere is on both sides, atmospheric pressure is on both sides. Then it would be 1/2 rho G H 1/2, oh, sorry, I did that weird. So if this was a rectangular wall, it would be 1/2 rho G H A, because this would be the average pressure, then you multiply it by the area. So if you keep each the same and double the area, you would double the force. So actually in that way, it doesn't matter because in both cases, force increases when area increases. So it doesn't matter whether it's on the bottom or on the side, but also the question said it was on the bottom. So if you clearly read it, you would have gotten that. So as I said, the force always scales with the area, regardless of whether it's vertical or on the bottom. Okay, so that's the point there. So now let's go on and talk about some new things. So we've got an object falling through a fluid. What forces are acting on that object? People put in the chat their ideas for forces acting on that object. Gravity or weight, yep. I'm going to call it FG, but it's also weight. Buoyant force. We just talked about buoyant force. And drag. Someone said pressure. So the pressure force on this, the sort of the static pressure force, that's your buoyant force. And then the pressure force that comes from the motion, that's the drag force. So there are pressure forces on this, and those get summed up in the buoyant force and the drag force. Okay. Alrighty. So then if we took the net force on this object that's falling is really just sinking in air. Yes, sinking and falling are the same thing. The sinking is just, honestly, most of the time when things sink in water, the reason they sink more slowly than in air is because the buoyant force in water is bigger. And so it's going to accelerate slower, but yeah, okay. So what is the net force on this thingy?
FG minus FD minus FB.
Okay, that is true when there's no acceleration. But when it's accelerating, the net force, or actually, never mind. I think you were right. I think I misheard you. So the net force is buoyant force plus the drag force minus gravitational force. Okay, that gets us our net force. And I've just defined this so that up is positive and down is negative, as how I define this when I set it up. Okay. And net force is mass times acceleration. So that's the mass of our object times acceleration. And you can replace acceleration with dv dt and all of these things. So the buoyant force is rho volume times g. That rho, is that the density of the fluid or the density of the object?
That would be the fluid.
That's the fluid.
Okay, someone just asked, would the drag force, like in water, be bigger than in air too? And yeah, it would. For the same velocity, the drag force would be bigger in water. Okay, and 1/2 CD rho v squared A for the drag force. Is that the density of the fluid or of the object?
Fluid.
Fluid minus mg. So just the weight of the object. So just as the object begins to fall, so let's say it's this and I drop it. Okay, so just as it began to fall, do you think that dv dt would be negative or positive? Okay. Positive, why do you say positive?
Because the velocity is increasing in the downward direction.
The velocity is increasing in the downward direction, and we defined down as negative here.
So then it'd be negative, sorry.
Yeah, yes. So you were right. The important thing is that you know that it's increasing in the downward direction, but just from the way we set up this math, that means that it would be negative. Well, and the reason why would be because when you first drop it, the weight would be bigger than the drag force, right? Could we just cancel out the m on both sides, someone asks? Well, the m is only in two terms. It's there and there, but it's not in this one or this one. So you could divide by m, and you would if you were doing the differential equation, but there'd still be m in there.
Doctor.
Okay.
Sorry,
Point is, right after you drop it, the weight is bigger than the drag force, but as the velocity gets more and more negative, it increases in the downward direction. What will happen to the drag force?
will increase.
It will increase. So as the drag force increases, it's going to start to cancel out the weight more and more and more. And finally, what will happen once the weight is totally balanced by the drag force and the buoyant force?
Terminal velocity.
You will get constant velocity. Okay. acceleration will be 0. You will have constant velocity. Okay. Just like this. That is the terminal velocity. Sarah asked, with downward being negative, we would need to say that g is positive. So in this class, whenever I say g, I mean positive 9.81 meters per second squared. And so then I just put the negative out front if I am trying to include in the equation that is pointed down. Okay. That is its terminal velocity.
I have kind of a question that I'm not sure if I can word it correctly.
All right, let's see.
So objects that float have a greater buoyant force than their
Weight.
But if you were to take one of those objects and like drop it into a little puddle, say, doesn't it like hit the water and then sink a little bit and then come back up and float?
Yep. All
so
right.
Is that because at first it's not fully submerged, and so, or how does that work?
Because it has a little bit of momentum when it hits. So it has some momentum. So I'm going to try to draw this here. So it's like this. It falls, it hits here. Right here, it has some v is equal to v naught. That would be pointed down. Okay. And so then you would do the same dv, and dv dt is equal to rho vg plus 1/2 cd rho v squared a plus the weight of the object plus weight. All right. So it's going to start right there. And because the buoyant, what direction would the drag force be pointing then? So it's just hit and it's sinking down into the fluid a little bit. So what direction does drag force point? Points up. Okay, so you have a little bit of drag force, you have the buoyant force. The buoyant force is going to be bigger than your weight. I'm going to call that minus W, sorry, for the weight. Okay. So your drag force is bigger than your weight, so your net force will be positive and it will be pointing up. So if the net force is pointing up, that means it's going to accelerate in the up direction. So it starts with a negative down velocity. It starts to accelerate in the up direction, so that down velocity gets smaller and smaller and smaller until it's 0. And then it will start accelerating in the up direction until it just hangs out on the surface. So it'll hit, it accelerates in the up direction, which means it goes down a little bit until its velocity is 0, then it goes down a little bit, and then it hangs out there. Does that make sense?
Yeah, so the acceleration at first is just slowing it down to 0, and then it starts
Yeah, it's just like if you threw a ball in the air, except opposite. Okay.
I have a question as well
Yes, Mara.
on that though. So if an object is sinking and it reaches its terminal velocity, so there's no more acceleration.
Yep.
How do you get something that like sinks to a point and then stops before the bottom? Because in my mind, it would just seem like it would just keep sinking at the same velocity forever.
Well, first, there is some friction. Friction happens. And second, so let's see. Okay, so there is some actual friction that's happening there, and we'll slow it down eventually, right? So that's why if you just throw out something, an object in space at 10 meters per second, it will go at 10 meters per second forever. Its inertia will just carry it along. Whereas if you could do that in an atmosphere with air, the air would eventually slow it down. So that's friction or drag, but let's see. So that would be, the buoyant force would be equal to the weight. And so in that case, those would cancel out, and all you would have would be the drag. And so the drag would the drag itself would slow it down until it stopped.
And then as it slows down, the drag gets smaller and smaller and smaller until the drag is zero. So
Yeah,
then
the
all
drag is slowing it down, and as it slows it down, the drag gets smaller until eventually it stops and the drag force goes to zero at the same time. Exactly.
And that's why the density of the object in the fluid has to be the same for that to happen.
Yes.
That makes sense.
All right. All righty. So now we have an example problem. Here we've got a paratrooper and his parachute. So we've got a round parachute, and I already looked at that drag coefficient table that I showed you before and found a drag coefficient for a round parachute. And I'm also just assuming an average air density. And I want to find the terminal velocity of the paratrooper. Okay, so I know that at terminal velocity, the weight of the paratrooper should equal his buoyant force plus his drag force. There is a simplifying assumption I can make at this step. What do we think it'll be?
Can we negate buoyant force?
Yes, the buoyant force is probably negligible in this situation because the buoyant force would be the weight of the air this paratrooper displaces, and the density of air is so small that it is probably not going to be significant compared to 950 newtons, which is, I forget how many pounds it is, but it's pretty heavy. So we're just going to make that simplifying assumption. What do we do next?
Do you plug in 1/2 c rho v squared a for drag force?
I'll do that, and I'll just call this weight 1/2 CD rho v squared a. And the reason we're plugging this in is because we want to find the terminal velocity. So we want to put in something with the velocity in it. That's how we do that. And now we can solve for the velocity. Root of 2w over CD rho a. What is a? In fact, I'm going to call it
Area of the parachute?
the area of the parachute. Who said that?
Me. Sorry.
Oh, hi, Connor. Yes, the area of the parachute. And by that, we mean the area in the direction of the fluid flow, right? So what would that be?
A circle of just
Yes,
whatever
which is
parachute diameter.
b squared, because it's a circle. Pi d squared, like that. Okay. And if you plug in numbers, you should get, I did this and I wrote down what you should get. I believe if I didn't make some mistake in my plugging in, you should get 4.93 meters per second, which is about 11 miles per hour. If you were on a motorcycle going 11 miles per hour and you hit a wall, would you be okay?
You'll feel a little jolted. And you might,
Yeah.
depending if you get hit in the head.
Depending, so that's a little fast, but it's not just going to smash you, which is how parachutes work. I was once hit by a car going about 15-ish miles per hour, and I was hurt, but ultimately okay, right? Because that is a speed we can survive. Okay. Oh, also incidentally, thinking about this parachute. So let's say you're falling and you're already at the terminal velocity of your body. Okay. And then you let your parachute go. So when you let the parachute go, what does that change about this equation?
It increases the area.
It increases the area. It'll change the drag coefficient a little bit, but most importantly, it'll get you a really big area. So you're falling at terminal velocity, you let that go, your drag force suddenly shoots up much bigger, which means you will accelerate up a little bit and that will slow you down. Okay, any questions about this problem?
And that acceleration is similar to the ball analogy, right? Because the acceleration is a lot at first because the drag force is high with a high velocity, but as you slow down, that acceleration goes to zero and you reach constant, right?
Yes.
Okay.
Yeah, it is, in fact, extremely similar to that floating ball we talked about. All right, here's another situation. So this time we've got a balloon. The balloon is filled with helium, and then instead of falling, it's rising through 20 degrees C air. So I'm going to approximate the balloon as a sphere, diameter 3, and I want to find its terminal velocity. There are some properties that I'm going to want to look up at 20 degrees C in 1 atmosphere. What are those properties?
Density of air.
Density of air, that's going to be important. What else?
Do you need the viscosity of air?
We actually will, and I'll tell you a little bit about why in a second. So yeah, I'm going to look up the viscosity of air too. Also the density of helium. And the reason I'm going to get the density of helium is because I'm going to need that to find my weight, right? Cool. So yeah, so I looked up all those things or calculated them from the ideal gas law for densities. Now, okay, the other thing I want is I'm going to want the, actually first let's set up our equation. So that net force equation is going to be, we have the weight Fg acting down, we have the buoyant force acting up, and we have a drag force. In this case, which direction will the drag force be pointing?
Down.
Down. And so that's going to change. So when I do my equation, force balance at terminal velocity would be force drag plus force gravity is equal to force buoyant. And in this situation, is the buoyant force going to be negligible? Probably not.
No.
Because, well, first of all, we just know that that's why balloons rise, is because of the buoyant force. So it's got to be significant. But also, if you look at the density of helium and the density of air, you should be able to see that the buoyant force is actually going to be bigger than the weight. And also that these densities are close enough together that they're both going to have an effect. Okay, so that'll be 1/2 CD rho. So for the drag force, do I use the density of air or of helium?
Air.
Air, because the drag comes from the air. Plus the weight, which will be rho times the volume times gravity. The density there, is that the density of helium or of the air?
Also of the air.
Okay, so this is the weight of the balloon. So will the weight of the balloon use the density of air or of helium?
Of helium.
Of helium, because the balloon's full of helium. Oh, there we go, sorry about that. So this is helium equals the buoyant force, rho Vg, and will that density be density of the air or of helium?
That one will be of air.
It should
Of
be
air, because buoyant force comes from the fluid around it. So yeah, remember to put the v squared a right there. I forgot about this. So I'm going to need the drag coefficient for the sphere. So I look here and I see that we have this equation for sphere. And for the special case of the sphere, it actually gives us drag coefficients for laminar or turbulent flow. So I'm going to want, so most of these will only work for turbulent flow, but this one gives us both. So I'm going to want to guess which it's going to be. I'm going to guess whether it's laminar or turbulent, and I'll use that drag coefficient. And then after I'm done, I'll check to see whether that was a good assumption.
Dr. Nickerson,
Yes,
so this table is only for Reynolds numbers higher than 10 to the fourth, right?
it is.
But is this laminar like an exception to that?
Yes, it's an exception to that.
Okay.
When it says for greater than 10 to the fourth, it means unless it says otherwise.
Okay.
Okay, so the spheres are a special case where it tells you this. Or if you were using this cylinder, that would be for laminar flow.
Yeah. Okay.
Okay. Alrighty, so I'm going to assume flow is turbulent to start out with. So I will assume that CD should be 0.2. And we will check after by calculating the Reynolds number once we have the velocity. Okay, so to put it again, force, drag plus force, gravity is equal to force buoyant, 1/2 CD rho air v squared A plus rho helium volume times G is equal to rho air volume times G, and A will be pi over 4 d squared, and volume will be pi over 6 d cubed. It's the volume of a sphere. And now I'm going to solve for, which actually I'm going to write that out. 1/2 CD rho air d squared pi over 4 d squared plus rho helium pi over 6 d cubed. I wrote that out so I could do that. Also, I'm going to multiply everything by 6 and we'll get, okay. So let's solve for velocity. So everyone take a second, solve for velocity.
Wouldn't it be pi over 8?
Volume of a sphere. Okay, so the volume of a sphere is 4/3 pi r cubed. So to put in 4/3 pi d over 2 cubed, so that becomes 4 over 3 times 8, because 2 cubed is 8, pi d cubed. So that becomes 1 over 6.
Thank you.
All right. And if you ever forget the volume of a sphere, you can Google it. Okay. So take it a second, solve for V. What do you get? Okay, so we have an estimate for the final answer from Rankin. So Rankin, can you tell me sort of symbolically what you got for V before you plugged in numbers?
Yeah, so I got 2 VG times difference of density of air minus density of helium over the drag coefficient times density of air times area, and then you square root the whole thing.
Yeah, that should, right, let's see, that's 1/8 divided by 6. So it'll be 3/4 times density of air minus density of helium times D all over CD density of air.
Shouldn't there be a G
Yes,
after the D?
thank you.
Okay, awesome.
Okay, I'm wrong. Looks like.
Okay, so you plug in that, and
I
then
think it's
you get
4/3 instead of
something. I'm not sure. I don't remember what number I got when I plugged things in here. But incidentally, this difference in densities, if you're wondering whether buoyant forces are significant, you can look at this difference in densities and it will always tell you. So if they're so different that one of them basically makes no difference from the other when you subtract it, then probably the buoyant force isn't significant. But if they're of nearish the same scale, then probably you need to include it. Okay, so you should assume turbulent velocity. So 4.12, I will assume that's right. You can check it if you want. 4.12 meters per second. And so then if I put that into the Reynolds number, I'm going to do a different color. Rho of air, V D over mu. And I'm using the density of air because we want the Reynolds number of the flow, and the air is what's flowing. So does anyone want to plug in that 4.12 meters per second with those densities? Okay, someone want to tell me what they got for the Reynolds number? Okay, 81,319. I'm going to simplify that as 8.1 times 10 to the 4th. So this is significantly more than, this is order of 10 to the 4th, kind of high up, getting on 10 to the 5th actually. So yes, this supports the assumption that this was turbulent flow. If we had plugged in the velocity we got, and we got some low Reynolds number, like 100, then what we would want to do is redo the problem using the drag coefficient for laminar flow, and we would get a velocity that was close to what we got, but more correct. Ian, yes.
Yeah, so in my book, the table says it's laminar if it's roughly less than 2 times 10 to the 5th.
Yeah, well, 8.1 times 10 to the 4th, I would say is roughly 10 to the 5th. But I suppose these things are guidelines anyway.
Okay.
And
so we would be
anyway, but if you're using that as the guideline, this is kind of questionable. But you should just have to choose an assumption and make a case for why it's reasonable or not. If that's why I used 100 as one where you would definitely know it was laminar. 1,000, you would know it was laminar. 10 to the fourth, transitional.
Okay, so we would be wrong then if we said we had to go back and redo it, assuming it's laminar.
Yes. Well, no, I wouldn't call that, for this, I wouldn't necessarily call that wrong, though you are using, yeah, if you redid it as laminar, I wouldn't necessarily call that wrong for this, though if you use this chart says 10 to the fourth. And so that just means that's the standard that they used when making this chart. So that's the standard you should use.
Okay,
Could you,
thanks.
Okay.
quick question, could you go over just what you were saying about the assumptions you make when the densities are very different versus very similar?
So if the densities are very different, so let's say density of air minus density of helium. Let's say in this case, that would be 1.204 for the air and 0.163 for the helium. So these densities are pretty close. The helium's about an order of magnitude smaller than the air. And so I would think that the buoyant force is going to be significant here. Okay, because one of those densities represents the weight, and one of those densities represents the buoyant force. And so when I put them together, they're about an order of magnitude different. I would say that's close enough that you have to consider both forces. But what if it was something heavier in the air? So what if it was like steel or something? And so then the difference would be, 1.204 for the air minus 2,000 or 2,000, 20,000. Let's say 20,000 to be unambiguous. Let's say this is metal or something. 20,000 for the density of metal. That's the difference between 20,000 and 20,001 is not really an important difference. So I'm going to assume that buoyant forces are probably not significant here.
Okay, perfect. Yeah, I just wanted to double check.
So just the more different, yeah, that's just it.
Dr. Nickerson?
Yes.
On the parachute example, if you had to calculate the Reynolds number, would you still use the diameter?
Yes, I would still use the diameter for that.
Okay.
That would still be sort of the characteristic scale of that flow.
So it doesn't matter as much if because when you said length in the Reynolds number, I always assumed it had to be going with the flow. Is it okay if it's like?
No, that is not, which one you use in the Reynolds number doesn't actually depend on whether it's going with the flow or against it. It just depends on which length scale is important for whatever thing you're talking about. So if we're thinking and talking about drag, then it's this area right here. Mm-hmm. That area right here is what goes into drag, right?
Yeah.
So I'm going to say that this scale here is what's important, and that this length going up like this doesn't matter as much. And so if this was not a sphere, but something like this, I would still use the diameter here because that's still the length scale that is important to the things I care about.
So that's the length scale that they would use when they were making the table. Is that right? And then you have to use like whatever they used.
Yes, you have to use whatever they use because the table is based off of experiments. So that's the number one thing, is that you just have to use what they use. And the number two thing is to think about which length is important to the phenomenon you care about.
Okay, thank you.
Cool.
And then that thing with the densities, could that also happen in reverse, where the buoyant force is significant, but the weight force is not? Like if you had a very light thing in a much heavier fluid, like if you had a helium balloon underwater, then you could say that mass times gravity, there's going to be very little mass to the balloon, but there's going to be a really big difference in the density.
You could say that. there would be essentially no weight, and that helium balloon would just go up and up and up and up and up until it left the water. And once it left the water, the buoyant force would go down some because it was in air, and then the weight would start being more significant again. But
Okay, perfect.
like, I agree with a helium balloon in water, probably the weight of it would not be significant while it was in the water. Okay, so last few minutes of class, we're going to talk about a specific phenomenon called creeping flow. And I hope people can stay a little bit late because I want you to know about this. Otherwise, you can watch the recording. So creeping flow. I have a question for you. Why does a bacteria swim differently than a human? So you can see the human swimming there, and the bacteria is just kind of waving its little things, its cilia. Why does it do that? Why doesn't the bacteria swim like a human swims?
No arms.
Well, it does have no arms, yes. You are right, it has no arms, but if it had little bacteria arms, it still wouldn't be able to do it actually. And the reason why, the human is gliding using inertia to carry them forward, right? So the human makes one big stroke where they're pushing the fluid back and then they glide along. Their inertia just carries them forward. The bacteria, if it had little tiny arms and it tried to do that, it just wouldn't go forward very far at all.
Is it an issue of scale, perhaps?
It is an issue of scale. Right. Good thought. Kyle, specifically is the scale of the inertial force versus the viscous force. Okay, so remember that's what Reynolds number tells us. So if Reynolds number is really, really small, the inertia is negligible, which means again, the bacteria would push down its little tiny bacteria arms and it would create a little amount of inertia, but just the viscous forces around it would be so big that they would just stop it and it wouldn't be able to go very far. And so that's why it does little wiggly
Well,
things and
let me
stuff.
ask you. So if say you put a person to that scale,
Uh-huh.
they would have to do the same, like they couldn't swim like a normal human would swim. They'd have
Yeah,
to.
exactly. If you took a person and
Really?
you shrunk them down till they were tiny, like the magic school bus or something, and
Right,
they tried to swim, they would not be able to. They just wouldn't go forward, and then they would sink. And the reason why is, remember, the inertia is rho v d or rho v l. Okay, so if this part gets too small, so if the arms are too small, then they just can't create enough inertia. Okay, I have lots of things I would say about Ant-Man and what happens when you scale things up and down, but I will not at this time. Okay, does not make any sense. Anyway, so we have flow that's very small, very slow, and or very viscous. So around bacteria, bacteria are about a micrometer scale. And micrometer, remember, is 10 to the -6 meters. So once you get down to the micron scale, you can start to assume this is happening. Okay, lava has creeping flow because it's super viscous and it's flowing very, very slowly. And there might be there can be some other situations where it happens. So really, really small things. Anytime something is really small, like micron scale or smaller, you should probably start assuming creeping flow might be happening. Okay. Creeping flow, you also call it Stokes flow, after a guy named Stokes who worked out a lot of the equations describing what happens when you get this kind of flow.
So Dr. Nickerson,
Mm-hmm.
if the bacteria was in like a river, say, like the river still has its flow, but then are you talking about in this case that would it still be in creeping flow like relative to the bacteria? Does that make sense? What my question is?
Bacteria, yes. So if we're
Okay.
thinking about drag on the bacteria, we care about the relative flow of the bacteria. That would have a pretty high velocity, but the bacteria is still so small, it would probably still be creeping. But then obviously the higher the velocity is, the less you would get this.
Okay, so because the length is just so small that the top part just kind of
Yeah, the top
drop.
part just kind of becomes insignificant.
Okay.
Okay. So negligible inertia means that the drag force is independent of density. Because we said rho v times whatever your length scale is, that's inertia. So when it gets that small, we can assume the drag force does not depend on the density. And so now we have, so without density, drag force is affected by velocity, diameter or length or whatever, and viscosity. So I want you to find the pi's. Tell me how many pi's you think there will be first.
2.
Okay, there's a process for deciding how many pi's there
It'd
will
just
be.
be 1.
Yeah, 1? Connor, did you say 1?
Yes, 1, because you'll need the FD and mu for the speed, for the time, the length, and the mass.
Yeah, because there's 4 parameters. There's mass, length, and time, 3 dimensions. 4 minus 3 is equal to 1. So we're going to guess there's only 1 pi. All right, so pi 1. Someone tell me when you got a pi 1.
So the thing you're trying to non-dimensionalize would be the FD, right? The drag.
That'd be the drag force. That's the thing we care about.
Okay.
And that would be mass times length over time squared. Yeah, how would you non-dimensionalize that?
So I would probably, let's see. What's the dimensions for viscosity again?
Okay, it is mass per length time. And if you ever forget that, you can remember that units of viscosity are pascals, seconds, and then you can work it out from there, but mass over length time.
Okay, so you definitely want to divide by that to get rid of the mass.
Yep, so let's divide by viscosity. That'll be mass per length time.
And then also by velocity squared, or
we want to get rid of that time.
Yeah,
so right about that. But is it squared?
I believe so. Or no.
Yeah, this time will go over there. You'll get 1 over time.
So you want to multiply by just velocity.
Yep.
And then divide by diameter.
Yep, because there will be 1. There you go. So if you have only 1 pi, what that means is that pi is equal to a constant. Instead of a function of some other pi, it's just equal to some constant. Who knows what it is? And you can't tell, from dimensional analysis, you can't tell what that constant would be. But that gets you, the drag force is equal to some constant times mu v d. The constant will depend on what the shape is. For a sphere, it turns out to be 3 pi. You could get that by, I believe you would have to integrate the shear stress over the surface area is how you would get that. But for a sphere, it's 3 pi.
So in the other case, we had 2 pi's because we had the Reynolds number and the drag coefficient.
Yep. Okay. So when you're not in creeping flow, inertia is important, density is important. You end up with 2 pi's. drag coefficient, and Reynolds number. In this case, the density drops away. You end up with 1 pi, which gives you this.
Okay.
Okay, so this was for Reynolds number less than 1. Basically, any Reynolds number less than 1, it is reasonable to assume creeping flow and to assume you can use this equation. So about 1 is the maximum where you would want to assume creeping flow. And this is what gives us, if you take some small ball and you drop it into a fluid, you can create a viscometer that lets you find viscosity from this. How would you do that?
Could you, if you know the mass of what you're dropping, could you time how long it takes to get to the bottom and then use that to find the force that must have been acting on it to counterbalance the gravity and then solve this equation for me?
Yes, Spencer, that is exactly what you would do. So you would say force gravity is equal to force drag plus the buoyant force. And when I put this in, you would say the mass gravity 3 pi mu v d plus rho of your fluid times the volume times g. And then you could, so you measure, you would have to know the density already, assuming that the buoyant force is significant, which a lot of times it would be in these situations because you're often trying to, so you would want to know the density already, so you could calculate buoyant force. And then you would measure the velocity by timing how long it takes to sink. And when you do that, you would kind of have to assume that it reaches terminal velocity pretty fast. And so if you just put it in the top, drop it.
So if you were designing one of these viscometers, it would be beneficial to have a longer one, right? So that
Yes.
the overwhelming amount of time it was at the terminal velocity.
Yeah, a longer one would make that assumption better. It would also, if you were just doing this with a stopwatch, which you can do, there's going to be a little bit of error from when you stop and start it. And the longer it is, the less that error will probably affect what you find, because it will be a smaller percentage of the total time. All right. Okay. And find the velocity, and then you can solve for the viscosity. And so that's how these falling ball viscometers work.
So does this drag force include pressure drag and friction drag?
Well, in this case, the pressure, we're essentially saying that the pressure drag more or less doesn't exist. This is going so slow, and the viscous forces are so big that the pressure drag is non-existent or negligible. So I think if this is something really super viscous like syrup, like maybe there's a little bit of turbulence behind it, but probably not a lot, because it's so viscous, it's just going to kind of close around it, and you won't get that low pressure weight behind it.
So is the pressure drag a function of velocity then? Or
the pressure drag is a function of velocity and of size of the whole thing. So just, yeah. So remember that the pressure, once it hits the surface, that's the stagnation pressure. So the faster it's going, the higher pressure you will get on the front of whatever your object is.
Okay.
Okay, so the pressure drag depends on the velocity, and higher velocity means more pressure drag, and then you get more, okay, and then, so higher velocity is more pressure drag. The more viscous it is, the less likely you are to get pressure drag. And then the
Okay.
bigger it is, the more pressure drag you get, because that gives you that area. And the bigger the area is, the bigger your pressure force is.
Okay.
So
that makes
that's why
sense.
we use the Reynolds number, because it puts it all together. So
Mm.
bigger is more pressure drag, faster is more pressure drag, and less viscous is more pressure drag. Though probably the velocity is the biggest thing that would change because it's squared. So the velocity is probably the
main factor.
the big factor. Like if I were just guesstimating, I would use the velocity to decide.
Okay, thank you.
But yes, but also, as I said, if it's like those bacteria, the bacteria can actually go pretty fast. They're just so tiny that you don't get pressure drag.
Okay.
Okay. All right, thank you. Sorry that that class went longer than usual. I did record it, so hopefully if people had to leave, they can come back and watch this. And I do record classes. Sometimes, I do apologize. Sometimes it takes me a while to get them posted because they have to, the Zoom has to crunch them and process them, and then YouTube has to process them, and it also makes them super low resolution when it uploads. So sometimes I forget to do that in a timely fashion, but I will make sure to do that today. Okay. Thank you very much.